In this video, I will explain what is second law of thermodynamics and how it is applied to a heat engine. It says that the second law of thermodynamics says that a process cannot occur unless it satisfies both the first and the second law of thermodynamics. And the second law also provides a necessary means to determine the quality as well as the degree of degradation of energy during a process. Second law of thermodynamics tells us about the quality and the degradation of energy, and it also says that no process can be completed until it satisfies the first law of thermodynamics and second law of thermodynamics. The first law was about the conservation of energy, and the second law says that there it is impossible for any device to operate on a cycle to receive heat from a single reservoir and produce a net amount of work. So it is saying that if we are receiving heat from a single reservoir, it cannot be converted into work. So if you want to have work, you must have two reservoirs. One is the source of heat, and the second one is a, sink of heat. So, in other words, we can say no heat engine can have a thermal efficiency of 100%, or for a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. So in this statement you can see that there is two uh, heat sources. The first one is the environment and the second one is furnace. Furnace is the heat source and environment is the heat sink. So this means a heat engine must exchange heat with a low temperature sink as well as the high temperature sink. So we need two temperature sources. This is the second law of thermodynamics, and we need to have two heat sources. One is at higher temperature and the second one should be at lower temperature to get a work output. So a heat engine is a engine which converts the heat to work. So how it converts the heat into work, it is shown in this figure, in which you can see here there is a high temperature source, which is a furnace. In the furnace we convert water into vapors or high pressure and temperature steam, which is passed through a heat engine, which gives us a work output, and a part of the that steam or heated steam is wasted into a low temperature sink, which can be environment or it can be a river at which the plant has been installed. So these are the basic steps that are involved in this uh, heat engine operation. So first one is that they receive heat from a high temperature source. This is the high temperature source. This source can be solar energy, oil furnace or nuclear reactor. The second step, they convert part of this heat usually in the form of rotating shaft. So heat is converted into work, and the work is being in the form of rotating shaft, like in the all the engines. The third process is they reject the remaining waste heat to a low temperature sink. So a part of heat is converted into work and the part is wasted into a sink. So this is operated on a cycle. That means that all these processes are in happening in a cyclic way. A steam power plant is a classical example of a heat engine, and steam power plant, as we all know, is an external combustion engine. External combustion engine means that uh, the source of heat is outside of the engine. Like this is a source of heat, which is a boiler. A boiler is converting water into steam. So this is the energy source, and which is out of the engine. Our engine is turbine here, and we can see here that boiler is producing high temperature and pressure steam, which is going to turbine, and turbine is rotating because of this steam which is entering at its inlet. And now, after getting work out, we are getting steam at low pressure and temperature at the exit of the turbine, and this low pressure steam and is passed through condenser. Condenser is a uh, equipment that is used to condense water, condense the steam. Condensation process is a process in which vapors are converted into liquid. So this is done by cooling down the steam. Cooling of steam is done with the help of fans or pumps. So the heat is transferred to the atmosphere. Then this condenser transfer water, and this is done by a pump. So pump is collecting water from this condenser and giving the high temperature water to boiler again. So in this way, this steam power plant is acting. So we are adding heat. Q in represents the amount of heat added at the boiler. Q out is the amount of heat. Q out, here you can see the amount of heat rejected at the condenser. W out is the work output which we have getting at the turbine, and W in is the amount of work which is consumed by the pump. So pump is getting a negative work and turbine is producing a positive work. So next we will explain the thermal efficiency of heat engine. So efficiency, you all know that, is the measure of performance of a heat engine. So it is the ratio of output to the input. In our case, the output is the turbine work. The rotation of shaft which we are getting at the turbine is our output, and input is our heat input which we are giving it in the boiler. So this figure explains us the two cases. In the first case, the source heat is 100 kilojoule, and its work output is 20 kilojoule, and its waste heat is 80 kilojoule. So we know that this is our output 20, and this is our input 100. 20 divided by 100 is 20%. So its thermal efficiency is 20%. In the case 2, the work output is 30 kilojoule and input is 100. So 30 divided by 100 is 30%. So in the case 2, the engine is more efficient, and it is having a thermal efficiency of 30%. So now we'll do example to understand this concept. In this example, heat is transferred to a heat engine from a furnace at a rate of 80 megawatt. So QH The heat from a furnace is 80 megawatt. So you can see here, this is 80 megawatt, and if the rate of waste heat is 50 megawatt. So determine the net power output. W net is equal to QH minus QL, which is equal to 80 minus 50. This is our work output, which is 30 megawatt. And we all know that efficiency is equal to work output, which is W net, and heat input, which is QH, so which is equal to 30 divided by 80. This is our thermal efficiency.